A massive star never dies alone. Sorry, it always dies alone. Because no matter what happened in its previous history, it has companions close at hand and its mass might have changed. But in the end, when that iron core goes down, it's by itself. And so the lesson I'm getting at, though, is that the helium core is what matters a lot when it collapses. And it can go through all sorts of evolution up to that. But if you know the helium core and rotation, you've got 90% of the universe, which is partly to justify why I'm going to talk on models based on single stars. But I'm going to talk about the evolution and death of massive stars. When they die, they explode or they make neutron stars or they make black holes. And all of those are interesting. And the kinds of black holes, the masses, spins, and so on that they make is important to everyone who's trying to model these sources. Be it by dynamical evolution, you need to know what the black holes were that you started with. Be it by common envelope, be it by association. So I think that some of the numbers I will give, which are really estimates, but you've got to ask the questions first and might not be best guesses to get going. And so let's get going. I didn't know this slide was regarded as classic when I down there developed the web. 3 years ago, I would not have imagined standing here with such a slide. In fact, I made some notes to that effect, and I'm still paying them off. With apologies to the people who did amazing work and made this happen. But these are the black holes that are known of from LIGO detections, neutron stars, and black holes from X-ray binaries. And you see they span a range of masses. This is 20, 40, I can't tell if it's 80 or 60 solar masses up there. And down here around 1.4 where you expect the neutron stars, and then there's a gap. And it seems to be a real gap, and it starts around 4 and maybe 5. And then we go on up and we have black holes. And the thing that just struck me when I saw this first event was, my God, it was a pulsational periodic supernova. Because what I'm going to discuss, one of the things I'm going to discuss is, every time you see a black hole above 30 solar masses, unless you made it somehow by putting two 15s together, but every time you see something above 30 that came from a single star, parent stability was involved. So this is the strongest evidence I have yet that pulsational parent stability supernovae exists somewhere. And in fact, there's quite a few of them close to the line here we think PPISN. And PPISN, as I will discuss, makes another prediction, and that is that there's another mass gap up there at 52. And it might be 53 or 4, it's not 60. And then that gap goes on up to 133 solar masses, and there won't be any black holes there. Unless you did put 8 and 8 together and 32 plus 32 together and somehow get there, which seems second and third order to me, but we're not to say. So my son is starting college, and I want to show him that I can do an integral and that it was useful for something. It's the only math I'll show you today. So take the initial mass function, integrate from m lower to m median, the initial mass function, and integrate from m median to m upper and solve, and you get the median mass of something if you have a power law initial mass function. And today I'm just going to use saltpeter initial mass functions. I know you can do better, but that's what I'm using. And so gamma is minus 1.35, and you find the median of some event that has a saltpeter IMF distribution is 4/3, 5/3. 5/3 times the lower bound. So if the lightest star to be supernovae are 9 solar masses, then the median supernova is 15. And if I retain this extra term right here for m upper, in fact it's 13. So this is where we start discussion today. The average supernova, median supernova, is quite light, 13 solar masses. Half of the supernovae below it and above it. All right? Now, in fact, stars have hydrogen envelopes sometimes. But by the time they get to be pre-supernovae, that envelope is expanded so much that its binding energy is about 4 orders of magnitude or 5 less than the binding energy of the mantle and heavy elements that you're trying to push off. In fact, some of the heavier stars, like this 25 solar mass star, the envelope is formally unbound. If you recombined all the hydrogen in the envelope, it would give enough energy to lift it off. It is hanging by a thread. Neutrino mass loss, acoustic waves, certainly any binary interaction is going to take the envelope off and leave you with a helium core. So in binaries, whatever, unless you're merging bare black holes, in binaries, you're generally going to be interested in the helium core, as I said before, and not in the mass of the whole star. Well, we can fit the helium core. In fact, it's a pretty good linear relation of main sequence mass, and it's pretty close to 0.45 times the mass minus 2 solar masses. And we take that linear function and multiply 5/3, and now we have to guess at the mass where you start making black holes. And part of the lecture today is that there is no mass where you start making black holes. There's a smear. But 18 fits with SMART's observations. It would include most of the supernovae we see. So if I started at 18, the median black hole would be 30 solar masses if the whole star collapsed. But I just argued that doesn't happen. The helium core is always going to collapse. And so 11 is the number, but if you uncover the helium core somewhere along the way, it's going to have mass loss, so that's an upper bound. And I'll give some numbers later, but 8 is a better number in the binary system for the median black hole. And I can stop there, and you'd have most of the answer already. We're going to try to flesh that out with more physics and models. That's a lot less than the average LIGO mass, by the way. And so either they're putting them together, or there's some selection bias or something to do with how you bring them together is mass dependent. But if you just look at the birth of black holes, you make a lot of light ones for every heavy one. So stellar evolution, in a nutshell, the black is most of the stars that we see go supernovae and the ones that have heavy elements. It's easier to think in main sequence mass. It's more accurate to think in terms of helium core mass. From 8 to 13, you have the Chandrasekhar mass. The core converges on 1.4, 1.5 solar masses. The burning shells are very thin. The hydrogen envelope starts almost just outside of the iron core when it collapses. These stars are very easy to blow up, and they make at least half, probably more than half of the neutron stars, as we'll be discussing in more detail. These are the most interesting, to me, supernovae. These make the black holes, most of them. They make the heavy elements that we're made out of, and they make a mixture of neutron stars and black holes. And people like Adam and Thomas and lots of others have struggled for the 50 years I've watched, well, not Adam, starting with Jim Wilson, try to blow these things up consistently, and I'm going to tell you how 4,000 of them blow up, not how any one of them blows up. Ambitious I am. To get there soon. Anyway, this is perhaps the most prolific band, and then there are things affected by the parent stability, which can pulse and lose mass, but eventually make a black hole, I think. Then there are those that there's no question about it, they just blow up and there's nothing left behind, no black hole. And then there are the things that are truly huge, bigger than 260 solar masses, that can make black holes bigger than 130 solar masses. So you can see right away there's going to be some kind of gap. Maybe it starts at 62, maybe it starts lower, where there isn't anything just because it blows up. And it's pretty robust, the physicists say. So why do things blow up? Adam, I think, made a plot like this. We have 1, 2. If you look at a number of different masses, 9 through 25 solar masses, here are the low mass stars, the high mass stars. You've got the iron core, this is the pre-supernova star, and just outside of it you have a variable amount of mass piled up. And if there's a lot of mass, there's a big gravitational potential energy associated with ejecting that, and more importantly, when it falls down, it creates a huge ram pressure that tries to turn a neutron star into a black hole. So, short summary, these make black holes and these don't. Adam will fill in the details. So, just going to the range of 8 or 9 to 12 is very complicated in terms of the nuclear physics and the flames and the off-center radiation and all of that. But because of degeneracy, it doesn't really matter. So I'll skip that complexity and just give you the answer. The pre-supernova stars, we've got a lot of them done, and they've been done perfectly because I did them. So they all look pretty much like white dwarfs with tenuous 10 to the minus 5 solar mass. That's a 10 to the minus 5 gravity envelopes. And here is the maximum baryonic mass of a neutron star, roughly. And so, I say to Adam and Thomas, if you can't blow up those stars, you should quit. Because they just puff. There goes the envelope, and there's a neutron star. A neutrino-powered wind, for example, would easily blow up this star. So I wish everyone would maybe get together and issue a statement. Half of the supernovae we see, we understand in neutrino power. So people would quit saying we don't understand supernovae. We understand half.
I'll give a variation on that theme.
You will. That's my time. With 260 solar masses is the difficult range. And because we couldn't do any one star correctly, we did 4,500 incorrectly. Or at least approximately, as sometimes we do in science. It's as good as we could do today. You go today. And we want Adam to blow up every one of these stars and tell us in 3 dimensions with full glory what it does. But today I make a guess, because he's not going to do it. I'm sure. So high resolution, lots of zones, 0.01 solar mass spacing, 15.01, 15.02, and so on. A whole lot of stars really densely covering the mass spectrum in this range. And I'll show you in a minute, it actually was important to do thousands of miles. You might. So the physics was sort of standard. Mass loss is very important, very uncertain in all of these studies, especially what you do for Wolf-Rayet stars. When you uncover the helium core, it shrinks, and the shrinkage depends on the metallicity and the mass of the star. Nobody knows exactly what it is. This is what we're using in my scale of metallicity of 0.25, my scale of metallicity of 0.89. Depends on who you take. Stars below 33 solar masses, solar metallicity in their lives as red supergiants. Those heavier uncover their helium cores and make Wolf-Rayet stars. So jumping, because I have a whole lot of time, right to the interesting part, here are the iron cores of those thousands of molecules. And there's a range where it's pretty well determined. And it doesn't depend too much on the mass loss rate that you put in. And there's other places where it's pretty well determined. And there's places where, what the heck is that? You change the mass, epsilon, 1,000 to the solar mass, and the star goes down a different path. Maybe it becomes a black hole, maybe it becomes a neutron star. Think about that. The Russell Boat theorem is dead. Okay, it's not determined by the initial mass. Chaos is alive. Lorenz said that if you have a system that you understand approximately, and it's a deterministic system, you know the physical laws govern it, and you know its approximate state. If you cannot determine approximately its future state, it is chaotic. So stellar evolution in some mass ranges is chaotic, and interesting transition point. This is where you start to ignite carbon burning. Below this mass, you ignite it with such vigor that the core convects. It changes the structure of the star. Above this, the carbon burning radiatively in the star. In between, there are 4 carbon burning shells, 3 oxygen burning shells, and 2 silicon burning shells. And they interfere constructively and destructively with each other. And they don't produce a continuum result. You could almost imagine a bimodal neutron star distribution coming out of that. I would. But, what the heck? Well, there is a measure of explodability where you assign some characteristic to the slopes of these curves. It could be the gravitational potential at 2.5 solar masses, which is essentially what Ott's compactness parameter is. And you find also that not just the iron cores, but the distribution of matter outside the iron core, which is going to make it hard or easy to explode, is chaotic from 13 to 19 solar masses. Below 13, it's not. The light stars I told you that anybody should blow up, those are straightforward. And they blow up, I'm sure.
I'm going to say something later.
Okay. But in between, there's a whole range of a factor of 3 in this compactness parameter. And the people who make such plots, calibrate them to their multidimensional explosions, would say some of these stars become black holes and some of them don't. And that's part of the important conclusion today. In this important range, where half the supernovae are happening, where the heavy elements are starting to be made, you can't tell whether a star is going to make a black hole or a neutron star, except statistically. If I do it versus helium core, I get a little cleaner plot. And it starts to be not so chaotic as multi-melting. That might be a better description. For a given helium core mass, there are 2 or 3 preferred solutions. And over here, well, a range and so on. But there's certainly, shall I call them attractors, there are places where the solutions tend to cluster. Okay, and why is this going on? Well, I'm not going to go into this because it would use up all my time, but this is the convective history of 4 stars in this mass range. And these are carbon convective shells, and these are oxygen shells and silicon shells. And where these little orange regions are can interfere with where the next orange region is, which changes the structure of the matter outside of the iron core, and either makes it have a big slope at 2 solar masses or a shallow one. And then these are stars where carbon burned radiatively. Instead of being cross-hatched, it's not in the middle of the star. So it's the convective shells in the last century of the star's life that are determining its explodability. So we took these thousands of models and we blew them up the best we could. Working with Thomas Young, we blew up about 300 of them in one dimension. Adam will tell you that's not really good. But we took a standard protoneutron star that they launched offline, took its luminosity, put it as a light bulb into a full one-dimensional neutrino transport calculation, determined what blew up and what didn't, and what was left behind, the neutron star mass, and so on. For the thousands of other models, we used parameterizations, and aside from Ott and O'Connor's compactness parameter, there are starting to be numerous works on how you might guess whether a star is going to blow up or not, just from looking at the pre-supernova star. And so a diagram of explodability might look something like this, taken from Erdl et al.'s paper. If the neutrino luminosity is high, and if the mass accretion rate is low, it's easy to blow up. I think Adam made a picture like this. And vice versa, if the mass accretion rate is high and the luminosity is low, it tends to be a black hole. Well, they translated that into two parameters that could be evaluated looking at the pre-supernova star, which was the gradient of the mass at the point, at the base of the oxygen shell, essentially, where the entropy was 4, and the product of that mass where the entropy was 4 times mu4. And they made an argument that the accretion rate scaled with mu4 and neutrino luminosity with mu4 m4. And so you can make a plot like this, which is a little different from the O'Connor plot. Above this line, things should make black holes, and below it they make neutron stars. And here are our thousands of models color-coded by mass. And so we think we can guess which stars are going to blow up, and then we can get checked in the future when people can do better calculations. Another work by Bernard Muller et al., they used 5 parameters to describe the pre-supernova star. We evaluated our models that way as well. And so, using 3 different approaches, here's the Erdl approach, the Muller approach, and then, of course, the O'Connor approach, we can, and also calibrated against 300 one-dimensional neutrino transport models, we can guess what stars are going to blow up and which aren't. The red ones blow up and the black ones don't. And as I promised, below 13, it all blows up. And above 26 or so, it all blows down. And in between, it does a mixture of stuff, but there is this peak around 20 where it all is all black holes. And you see that in the other parameterization as well. So you get a mixture between 14 and 20, no black holes below 14 solar masses. If the whole star implodes, which, as I would argue, is not likely, but no black holes below 4 solar masses if the helium core is what implodes. So that sets our lower limit, essentially 13 solar mass stars. And then the 26 solar mass star is the place where everything becomes a black hole. Now, evaluating the neutron star masses and comparing to observations, we get good agreement. The average neutron star mass, gravitational mass, 1.37 solar masses. Okay. Now, in interacting binaries, and I'm well aware that when you see gravitational radiations coming from interacting binary, things can be different because the helium core is uncovered earlier on, maybe at the beginning of helium burning when the star tries to become a red giant. So there's more mass loss as the helium core evolves and burns helium as a bare helium core than there would have been if it had kept a shrouding envelope on top of it. And so in the end, some of these masses would be smaller in binaries than they would be for single stars. But because these are coming from such low mass stars where the Chandrasekhar mass is playing a dominant role, I don't think it would vary very much for neutron stars. For black holes, it varies a little. Now, there is another group of stars that blow up, pulsational peristability supernovae, and I have to be very quick here. I've given talks on this before. From 30 to 65 solar masses of helium, there is an instability that shows central temperature as a function of time to collapse, where the star begins to pulse violently and explosively burn oxygen and silicon and carbon. And with each pulse, it ejects some mass from the surface. And this can go on for days to millennia, depending on the mass of the star. But in the end, it has ejected all of the hydrogen envelope and part of the helium core, and this is what is left behind if you were able to collapse the entire star, which you could not do in a close line, as someone reminded me. You could get a black hole of 70 solar masses, and that's the biggest black hole you can make until you get up to 133. Okay. Even in single star systems, 70 is the biggest. But in binary systems where the helium core mass is what's governing, you will evaporate everything below 52 solar masses, and there's nothing above that. Putting all of this together, as I must soon, here are the neutron star remnants. This is for no mass loss, so this is an extreme case, may be appropriate to top 3 stars, if even there, because top 3 stars may have mass loss. But for a star with no mass loss, this is the hydrogen envelope, included the whole star, and you get a peak at 70 solar masses. For the helium cores, including the pulsations from pulsation pair, you get a maximum of 52. So 70 for single stars, 52 for binaries. And then we weight this by an initial mass function, saltpeter in this case, and we get the average masses. There is a cutoff at 52 for pulsation pair. Average 9.8 solar masses if the helium core collapses, a bigger number if the whole star did. But isn't this curious? Now I have to tell you, truth in advertising, this is a logarithmic axis. So these are small numbers. But yet, LIGO C, black holes here. There is not just a cutoff at 52, there is a bump. First time this has been called attention to, I think between 30 and 40. You might be able to see it. That would be neat. So there was a bet. I'm surprised anybody brought up yet. You can't decide, you make a bet. So the signatures, Belchinski, Holtz, and others, Ilya's the witness, and the witness is, the bet is that in 100 LIGO events, no black hole will be found over 55 solar mass, essentially. And that's cheating, I think, because 100 events is 200 black holes. But nevertheless, I took the bet. Okay, moving on to solar metallicity. Same sort of plot. These are the final masses, but now the helium core is uncovered above 33 solar masses. We have Wolf-Rayet mass loss, and what you get depends very much on the Wolf-Rayet mass loss rate. And here we're taking Transons and Dakota 2016. If we multiply it by 2, we don't get anything above 20 solar masses. If we leave it alone, we begin to touch the pulsational pair stability masses, even in solar metallicity. And if you go down to half or a third solar metallicity, you'll start getting into those. So this is for the stars of solar metallicity, and if the helium core collapses, 9.8 masses for the average black hole, but a distribution going from 4 on up to some upper limit that's very mass loss sensitive. If the mass loss rate is twice as big, the average is 8.6 instead of 9.8, and things cut off, here instead of there. And of course, this could go on down to 10 to the minus 4 for 160 solar mass star. So there might be a few events even up here. But we're getting into places where the mass loss rate is totally uncalibrated. Who knows? If I try to guess what binaries might really do, let's say you've got an interacting binary, and every time any star tries to become a red giant, it loses its envelope. So let's just say every star becomes a helium star at the beginning of helium burning. But it is subject to Wolf-Rayet mass loss. We do that. Then you get a distribution that looks something like this, the green points, and the average moves down to 7.8 solar masses for interacting binaries. Sometimes it's important to ask questions, even if the answers are very quantitative. This can all be fleshed out with a lot more calculations, both with supernovae and pre-supernova evolution. But I think these masses are things that we're starting to be able to comment on. And they don't vary a lot. So summing it all up, as I must, for full star collapse, which I hold is unrealistic, you could get black holes up to 70 solar masses with no mass loss, but more realistically, 32 solar masses for solar metallicity. And the averages are quite high. But if the helium cores are the things that collapse, everything's in a pretty narrow range from 7.6 to 10 solar masses. So kind of robust prediction here is that your average black hole mass is sort of in the 7 to 10 solar mass range. But the extrema can be quite different depending on what the mass loss situation is and what the binary situation is. It might go up to 51, it might stop at 15. So the upper end is uncertain. On the other hand, that's something that if you measure, you'll tell us something we don't know. And that's, I think, they have full place. So conclusions. I'm okay. Yeah. So conclusions, 14 to 19 solar masses, evolution is chaotic. You need to do it statistically. If Thomas, to name someone besides Adam, takes a model from Ken Nomoto and from me and from the Italian group, Chiasi, and from Hirschi, and they all say 15 solar mass models, they're not the same. I mean, we can take a 15 solar mass model and run it on 2 different machines and get different answers. I'm sorry to admit. So it's that chaotic, and you're not going to be able to say 15 solar mass star does this, 18 solar mass star does that. You're going to have to statistically analyze it and say a third or 2/3 of the time, 15 plus or minus a half does this, and so on. Well, that's interesting. It means a lot of work is ahead. All black holes in interacting binaries, 3.5 to 52 solar masses. You know, feel free to shoot these numbers down, but at least there are numbers to work with. Maximum mass black hole, 70 solar masses. Median black hole in interacting binaries, 7.5 to 10.5. Average neutron star, 1.37. Black holes with masses bigger than 30 all come from pulsational pair instability supernovae. GW150914 suggests there was a pulsational pair instability along the way. The fraction of stars collapsing and making black holes is bigger in single star systems than it is in binary systems. Because the general thing is you uncover the helium core earlier on in the evolution in the interacting binary. And so it has time to lose more mass as a Wolf-Rayet star. And so in the end, it's more likely to make a type 1b supernovae than to make a black hole. And so the explosion probability, I had it a while back. It was, I think it was, for the bare helium cores, 5/3 blow up and 5/6 blow up and 1/6 falls down. And for the single stars, there's twice as many that collapse. Now, I haven't talked about Kerr parameters. Someone would like this slide. Here are chemically homogeneous evolution models with nominal fast rotation, 60 through 90 solar masses, ending up at 50 through 70. You can get Kerr parameters up to maybe 0.2, but they tend to be around 0.1. So we would expect slow rotation, but if chemically homogeneous evolution is going on, there might be some fairly rapid rotators. And there needs to be some stars somewhere that make gamma bursts. And if the collapsar model, if it's going to work, some of them need to have Kerr parameters pretty close to 1. And then finally, 10 supernovae a second in the universe. I heard yesterday that maybe we're going to see all of the mergers in all of the universe. Maybe we live in interesting times. Thank you.
I'm sure there are lots of questions. Roseanne.
I have 2 questions. One of
Did you
them,
do that?
Yeah, you can.
well, thank you.
Well, one minute.
She needs a mic.
Sorry.
One of them has to do with models we're considering now where you might have a 3rd star that has not yet evolved once you form that compact object binary. And the 3rd star can donate mass.
Yeah.
So that would have the potential to, let's say, take a black hole of a mass that you can predict from your models and turn it into one that may not naturally emerge even from the binary models. So my first question is whether, we're trying to see, is this testable? How would you know that it had mass transfer? So I'm asking whether your models predict combinations of masses for double black holes, where if we saw something that differed from that, you'd say, I don't think you can do that through a supernova. I think you probably had to do that by gaining mass in some way.
I don't think I have this succinct answer you're looking for. There are predictions like this mass gap from 52 to 133, but things that are as specific as that. What I'd say we can contribute is we can tell you what the final evolution of helium cores of different masses are going to be. So take your 3 stars and evolve them to what you think is the end, and we can tell you what it makes.
I see.
And then you can plug it into whatever algorithm you have.
Right, maybe a probability.
To get what the trickle
analysis.
fraction is.
Well, thank you. And so my second question is, I think your results here are one of the most intriguing results in science right now, where you're showing that in these general, seriously, because you're showing that there's chaos in what we
Yes.
thought would be a fairly straightforward system that we teach in
I
classes
thought that
all
was
the time.
cool.
It's very cool. So my question is, there are certain elements that you're talking about that seem to lead to this. Where else in stellar astronomy should we be looking for this type of
Chaos?
effect? Yes, I mean, there are a lot of variable systems, a lot of events, a lot of strange
I don't
things.
know. I strongly suspect it exists in many places. But, I like Lorenz's definition. If you have a system where physics and well-determined laws are governing it, and you know its state today, but you can't predict its state in 2 weeks, e.g. the weather, it's chaos.
Avi,
So Stan, massive stars are often in binaries.
I'm told to stay behind the weather.
That's okay. So if you have a binary of 2 massive stars, and one of them goes to a black hole with a mass gap that you predict, the mass limit, could you envision a situation where there would be accretion from a second very massive star such that you will feel the mass gap at the level of, 100 solar masses or more?
Hadn't thought of that.
I don't think there's enough time.
You'd have to have a lot of mass accretion.
Yeah.
Have a superhead.
2 massive stars,
It would have to be
Not enough time.
accretion.
Highly superheating them because you don't have much time, right? The second star is going to finish its job very quick.
A few million years.
Yeah, 2 million years.
Yeah.
So you have to be
3 million.
extremely superheating.
It's always 3 million.
Okay, so it's 10%, I see. You're saying it's 10% of the Eddington
of
time.
the solving.
Yeah, okay, that's a good point.
but it could be more if you're, in incredibly dynamically unstable mass transfer. The Eddington limit doesn't matter. So I think it's actually.
Yeah, so go
So
for
you
it.
could know
Doesn't
where-
papers about how we predict it.
But let's go on. Other question, one more question, maybe 2? Yes, Vicky?
Stan, would rotation affect the parent stability mass laws when it triggers? Will it affect your upper mass limit?
So you say rotation affect the mass?
Yes.
But definitely.
So these mass limits for fast rotating stars, not necessarily chemically homogeneous, but just fast rotating.
Well, it's a very important question. It could lead down a very long discussion. But in general, rotation in massive stars looks like it increases its importance as you go to heavier masses. That is, down at the lighter end, it has to do with Eddington Sweet time scales. Years ago, Alex Hager and I did a study of different mass stars with magnetic torques included. And we found that as they went to the heavier stars, they rotated more rapidly. The lighter stars, which make the neutron stars, did indeed give rotation rates comparable to pulsars. But if you went up to 30, 40 solar masses, it rotated better. So I think you're more likely to see the effects of rotation at very high mass. And we really, we barely have an empirical model or data for spherically symmetric mass loss and output. Rotational, obviously it rotates at critical rotation. You could have mass shading at the equator. But yes, it's important, and no, we don't know.
We're going to have to cut off the discussion. Sorry, there are lots of good questions. Now, let's thank Stan again.